The quicksort that you've seen in the previous videos was not in place. Remember, in place means that we use only a constant amount of additional memory, which is in addition to the data structure that we're provided. So with an in-place algorithm, we don't create any additional data structures. We work directly on the data structure that was given. With the previous quicksort implementations, we ended up creating additional lists L, E, and G, which kept track of everything less than, equal to, or greater than a particular pivot element. We can implement this in place without creating those extra lists and work kind of directly on the input sequence just by maintaining our constant amount of additional memory. We'll just keep track of where in that list our greater than, equal to, or less than elements are. So this is what our in-place algorithm for quicksort does. So we're gonna, given a particular sequence and a left and a right kind of lower and an upper bound of this, so because this is in place, at some time we may only be working on a portion of our sequence. So let's say we're only working on, here's L and here's R, and we're not working on this part of our sequence, we're only working on this reduced portion of our sequence because we're going to make recursive calls and do this for smaller and smaller sized portions of our sequence. So given this part of our sequence that we're working on, our in-place algorithm will, provided we have a large enough size, meaning that these values don't overlap, we will randomly pick some integer in between these values. This will be our pivot. So we randomly pick a pivot, and that element stored at our random index will be x. And we use x in order to partition this part of our sequence into L, E, and G. So we want to kind of partition this so that we have in place partitioned it into L, E, and G, where everything on the left here in L is less than our pivot, equal to our pivot, and greater than our pivot. And in order to do so without creating separately these lists L, E, and G, we're going to maintain them directly in our given array so that we have, as a result of our in-place partition, beginning with L, ending at R, using X as our pivot element on our sequence S, we're going to return indices H and K, which tell us where in this portion of our list that we're working with, where we have separated L, E, and G, directly in the structure we're given. So we're going to have that the less than list will go from L all the way up until H minus 1. Our equal to list will go from H up until K, and our greater than list will go from index K plus 1 all the way up until R. So H and K are just indices, so rather than creating those lists separately, our constant amount of additional memory that we're using is just keeping track of these two indices give us where in our data structure that we're given, where in the array that we're given, we've already swapped elements so that we have the less than list appears from L to H minus 1, equal to appears here, and greater than appears from K plus 1 to R. Okay, and then once we're given those, we can recursively call our in-place quicksort on, this is recursively calling it on that list L, and recursively calling it on that list G. Okay, so how do we implement this in-place partition? Okay. We can do this in two steps. So I'm going to show you the first step here. And the idea here is that we're going to split our list into, in one step, we're going to split our list into everything which is strictly less than our pivot and everything which is greater than or equal to our pivot. If our pivot is X, say. And then this would be our first step, and then we can use the same idea in order to partition this right portion into, separate this into everything which is equal to or greater than our list. So in just one step, we'll partition and find everything less than our pivot and everything equal to or greater than our pivot. And then by calling this again, we can partition just this equal to or greater than into equal to on one side, greater than on the other side. So how would we partition this into just less than or greater than or equal to? So given our sequence, we're going to and we want to do this in place again, so we're going to work directly on the structure we're given. Keep track of two indices, h, which will start at the beginning, and k, which will start at the end. Now we're going to increment h so that once it reaches an index where it finds some element which is greater than or equal to our pivot, it'll stop there. Now what we want to do by incrementing h and decrementing k is we want to reach a point where we have, let's see here, where we've got from 0 to h minus 1, we want to be all of the items strictly less than x, and then from h up until the last part of our list, this will be everything greater than or equal to x, our pivot. In order to do that, we're going to, starting with h at the beginning, increment h until it finds something greater than or equal to x. So in this case, let's say, so x is our pivot, let's just say that we picked 6 as our pivot. So x is 6. This is just something which is passed to our in-place partition method. So first we compare at the beginning, h is 3. Is 3 greater than or equal to 6? No, which means it's less than 6, so it belongs on this left side. Now we move to the next one. H is 2. We compare 2 to 6, it's less than 6, so it belongs on this left side. We move to the next one. And we keep incrementing every time, comparing whatever h is pointing to our pivot, which is 6. And if it's less than 6, then we're in the clear. We've formed up everything here is less than our pivot. And we stop once we reach that h is pointing to something greater than or equal to our pivot. But before we do anything there, we just stop incrementing h. Now we know h points to something greater than or equal to our pivot, which means it doesn't belong on this left side. So we're going to swap it, but which thing should we swap it with? So this is where k comes into place. So we have some kind of a loop here to increment h until it finds some element greater than or equal to x. So when we're finished with this while loop, h now points to something greater than or equal to x. And now we're going to have a consecutive second while loop. K starts at the right side at the end of our list, whatever portion we're working on, and it will repeatedly decrement until it finds some element less than x. So starting at the end here, we compare 9 to our pivot. It's greater than or equal to our pivot, which is good. That means it belongs on the right side. Now we decrement k. We compare to our pivot. It's greater than or equal to our pivot, which is good, which means it belongs on the right side. And we keep decrementing k until we find some element here where now k is pointing to a value which is less than our pivot, which means it doesn't belong on this right side. Instead, it belongs on this left side. So we stop decrementing k here. Now h is pointing to something which belongs on the right side because it's greater than or equal to our pivot, and k is pointing to something which belongs on our left side because it's pointing to something less than our pivot. So these two values, where h and k point to, we're going to swap. So now we have 2 belongs at this position, and 7 belongs at this position. So we had here h is pointing here, and k is pointing here when we're finished. And then we repeat this process. So until h and k cross, meaning that we've already separated appropriately everything less than and greater than or equal to our pivot, until h and k swap, we're going to keep, until they cross, we're going to keep performing this operation. So now h is pointing here. We have built up so far everything on the left of h is strictly less than our pivot. Now we're going to increment h again until we find some value which is greater than or equal to our pivot. And then we stop there. Now we move to k. We decrement k until we find some value which is less than our pivot, and then we stop there. Now once h and k cross, we know that we're done. We've appropriately separated items. But if they haven't crossed yet, we may have to swap elements a few times in order until we get to that point. Now our total running time here is still big O of n, and the reason for that is, in the worst case, we end up swapping each element, kind of going through each index once, but we start kind of on one side of our array and the other side of our array, and no matter where we k and h join, maybe it's in the middle or maybe it's over here somewhere, we still only go through our array once from the left and from the right, which means in the worst case we swap at particular indices no more than once, and we have n of them. So our total running time here is still linear. So this gives an in-place method, an in-place implementation of quicksort, because we have an in-place partition, which is one of our subroutines used in quicksort. Okay, so how does quicksort fit into the sorting algorithms that we've encountered so far? So you've seen now selection sort and insertion sort, which run in quadratic time. And now quicksort, we have an expected running time, which is big O n log n. But still, keep in mind that the worst case running time is n squared. This is if we're unfortunate that we pick a bad pivot each time. We don't expect this to happen, but it's still possible. But we can implement this in place, you just saw, but this isn't stable, and again, this comes from when we are swapping elements. But this is pretty fast. This is good for large inputs, same as heap sort. Now what's kind of hidden here in our big O notation is what constant coefficients come here. And if we were to compare directly that, our randomized quicksort versus heap sort, randomized quicksort would outperform it. Still, merge sort is better for huge inputs, and the reason for that is because it gives sequential data access. So if we have so much of a large input that we can't store it all in memory, then easier for merge sort to use that we kind of break it up into chunks, just those chunks that we're going to work on directly, load that into memory, and then kind of save it off and work on the next chunk. There is one sorting algorithm which kind of combines all of these. I believe it's called timsort, but since we have each one of these sorting algorithms works for particular sized inputs, this timsort algorithm will determine based on the input size which algorithm to run. So for example, if this is huge, it'll use merge sort, break our input into smaller size chunks, and then for those smaller size chunks use, for example, quicksort. And then once quicksort works its way down to a small enough sized input, it'll use on the remaining small sized input insertion sort, for example. But this is just one way you could put all of these together. But what you should take away from these videos so far is that we have a variety of ways that we can solve sorting using different methods. We've seen a few divide and conquer paradigms, algorithms based on the divide and conquer paradigm so far, and even one which uses a randomization, an element of randomization. But we haven't gotten better than big O n log n so far. So initially we had some maybe naive approaches which ran in quadratic time. And then so far the best that we've encountered are algorithms that run in big O n log n time. So is it possible to do better than this? You should always be wondering, can you do better? Can you make some algorithm even more efficient? And we'll see in the next video if this is even possible.